All right, so today we are going to talk about the transformations in mathematics. Now, there's three of them that exist. One is a translation, and that's basically where you just move a figure. And then next we have a reflection, which is basically flipping a figure or mirroring it. So you basically just flip it from left to right, up or down. And that these always reflect about line. And then next we have a rotation. So when you take a figure and rotate it, you're literally rotating it about a point. So what we're going to focus on today is just the translations. And we need to figure out some vocabulary first. So when we take a figure and we decide to do a transformation on it, there's two key words here. When you have an original figure, we call that the pre-image. So if the pre-image is the original figure, then the image is the new figure after the transformation. When we name the image, we use prime notation, and I will discuss more what that looks like in a moment when we actually do a transformation. So yes, a translation is when a point or figure shifts. So we're moving a figure anywhere that we want to on a coordinate plane. So our next keyword is the congruence transformation. What is that? Well, we know what a congruent means. It means that you have two figures and they have the same size and shape. Well, a congruence transformation is going to preserve the size and the shape of a figure. So that keeps the two congruent, size and shape of a figure. Now we call this phenomenon an isometry. Isometry. So in this theorem right here, the translation theorem, all we're going to say is that a translation is one of the types of isometries that we see in a transformation. So a translation is an isometry. So what this looks like is, well, if you take a pre-image, in this case we're just going to make a basic triangle, we'll call it A, B, C, and let's say I just decided to shift it over, preserving its size and shape. So I'm just going to shift it over to the right in this case, and I'm going to call this triangle, because this is the image, this is now going to be called A prime, B prime, C prime. Now because this is an isometry, we can now say that triangle ABC is congruent to triangle A prime, B prime, C prime. So this is the new notation. The A prime, B prime, C prime says this is the new image. So in this first example, what we're going to do is write a rule for the translation. Now, when we write rules for our pre-images to the image, we use coordinate notation. So I'm going to go and write that out. And what does that look like? So with coordinate notation, you basically take your ordered pair, x comma y, and it's going to change its position to whatever I want it to do. In this case, I can take any of the x's or all the x's and add it to a value. Let's call that A. And then we can also take any of the y's and the y coordinates and add that to some value, and let's call that B. So you can add or subtract any value that you want to, and it will always preserve the image. So all the points will map to a new position. Okay, so when you look at this figure here, the original figure is the one just called ABC. So the transformation is the A prime, B prime, C prime. And we want to write a rule for this. So to write the rule, we're going to go ahead and start with x comma y. We're saying, okay, for every coordinate, x and y, what happened here? Well, I'm going to go take a highlighter, and if you just map out from A to A prime, B to B prime, C to C prime, it will tell you where is the movement. And we can already see right now that it definitely shifted up and then back. Well, let's see how many units that was. Just take one of the figures, one of the points. I'm going to take A, and notice that we're just going to map out where did it go here. So according to this, A going to A prime went up 2 units, and then it went back 3 units. So what does that mean? It says that the rule for this, you take all your x's and you're going to go back 3 units. So we were going to go x minus 3, comma, for all y's, we went up 2 units. So we're going to add y to 2. So that's the rule of this transformation. And you can check by checking all other points. So let's look at B. We went up 2, back 3. Yep, and there we are. Let's do C. Up 2, back 3, and it put us in the new position. So to verify that this is an isometry, what we're going to do is just prove that these two triangles are congruent by either SSS or SAS. I'm going to go SAS on this. So I'm going to go ahead and get the distance of AC, and I notice right now AC is 3 units, A prime C prime is also 3 units. So AC is equal to A prime C prime, which is equal to 3 units. Notice right here, BC is 2 units over here, and then B prime C prime is the same. So CB is equal to C prime B prime, which is equal to 2 units. And, you know, I can find AB for both by doing the distance formula, but I'm just going to go ahead and use SAS because I can see that AC is perpendicular to CB and A prime C prime is perpendicular to C prime B prime because, yes, they have opposite reciprocal slopes at those points right there. So by opposite reciprocal slopes. So yes, this is definitely an isometry that has happened here because triangle ABC is congruent to triangle A prime B prime C prime by SAS. All right, so in this next example, what we're going to do here is actually have a pre-image, and then we're going to use the rule that's given to us for the translation and then draw out the image that was produced from here. So the quickest way to do this that I prefer is take all the points that you're going to graph. So P is at 4, 2, Q is at 6, 2, and then you have R is at 4, -2, and then take your rule here. The rule says for every x minus 4, for every y, add 1. So from the image, or the pre-image to the image, we're going to say that P prime, for every x minus 4, so 4 minus 4 is 0, and then for every y, add 3, so 2 plus 1, or sorry, 2 add 1, 2 plus 1 is 3. So next point, we're going to do that one more time. So Q prime should be sitting at -4 for this from 6, that's at 2, add 1 to 2, that's at 3. All right, so for R prime, this is going to sit at 4 minus 4 is 0, -2 plus 1 is -1. And then after this, graph it. So we're going to first graph PQR. So PQR is at 4, 2, 1, 2, 3, 4, up 2. Here's P. Go to Q, so 6, so that's 6 up 2. And then R is at 4 down to -2. And then go ahead and make a triangle out of those 3 points. And then we graph our image. So P prime should be at 0, 3, so P prime right here. And then Q prime is at 2, 3. And then R prime is at 0, -1. So very fast and efficient if you can just list your values and then graph your image and your pre-image. Now, of course, you could just first graph PQR and then do for every point, go back 4 and then up 1, and then do that again for Q. But it's kind of silly because sometimes, again, the numbers never lie, and that's part of your showing your work, and sometimes people, unfortunately, count incorrectly. So the other thing that I like to do is color in my new image, and let me go ahead and grab a color here. I just like to shade it in really fast, and that kind of helps visualize, okay, that's the new image that has appeared, and it is just right here. So sometimes people shade those in just to really see where the translation happened. Make it pop out more. All right, so on the back side, we're going to talk about vectors. So what is a vector? We use vectors in mathematics to kind of just show where points are going, and the notation for this is a lot shorter. So a vector has two parts. It has it's a quantity that has both magnitude and direction. So size and direction. Okay. We use what we call component form to show a translation rule. And I'll talk about this in a moment. Component form. So component form is very short and sweet. It literally looks like this. You take a bracket and you have an x value. This is going to be your horizontal component, where is the point going from left to right. And then you have your vertical component, which would be the y, and that's telling you where is the image going from up or down. So what a vector is, it's just when you see one, it's basically like a little ray. And again, this is telling you where points are going. And then this is just one example. You can take a shape and move it about a vector. So when we name a vector, we use this arrow with like a half part or an arrow on top. So it's a line with an arrow on top, and that just tells you where is it going. So the way we name this is by 2 points, F, G. So F is your initial point. That's where we start. And then G is the terminal point. And the terminal point is easy to find because it's the point that is where the arrow is. So look for the arrow. Okay. All right. So I'm going to go ahead and highlight who we're focusing on because there's so many different lines in here. But the vector we're talking about is this one right here, FG. Okay. So in order to write the component form of this, we're just going to write it in our brackets, and we notice right now that for every for F we went 5 units to the right, so that's our horizontal component, so we're going to go 5 comma, and then the vertical component is that it ended at G, which is 3 units up, so 5 comma 3 would be our vector or component form. So it's really easy to name a vector. You just have to look for who's the initial point, where's the terminal point. In this case for A, it's going to be called GH. And then the component form for this, we're going to go ahead and just count where did it go. So from G to H, it went 1, 2, 3, 4, 5. So that's our horizontal component. And then it went down 2. So we're going to say down is going to be our -2. All right, now this one, I want you to be careful here. We start at R and we end at S, so it's called RS. So that's our vector. And the component form for this, from R to S, we went 1, 2, 3, 4, 5, 6, 7 units back. So that means it's going to be a -7. And then because there's no vertical component, we just put a 0 there. Okay. All right, last but not least, you guys go ahead and give this a try. But because I have to cut this video short, the answer to this, so VW is this vector here, so VW, and where did it go? It went 1, 2, 3, 4, 5, 6, 7 units on our horizontal component, so back 7, and it went down, let's see here, 1, 2, 3, so -7, -3. And then this one right here is going to be called AB. And then the component form of that, we went 1, 2 units horizontally, so 2, comma, and then we went down, let's see here, 1, 2, 3, 4, 5, 6. So we went down, meaning we're going to have a -6 for the vertical component. All right, so real quick, go back to the front page, and what we're going to do here is we're going to write out this rule that we saw in example 2 in our vector or our component form. So this in component form is going to look like this. For every x, take away 4, so that means we're going to go back 4 horizontally, so -4, comma, for every y we added 1, so it'd be -4, comma, 1 in our component form. All right, well, that's the end of our lecture today, short and sweet. Good luck on the assignment, and thank you.